Okay, welcome to Math 254, Intro to Linear Algebra. And one thing that I always get feedback on is that I don't solve enough problems in lecture. And we have this fantastic new thing on campus called Learning Glass. So what I'm going to do is I'm going to record lots of problem-solving sessions that you can see at any time. So we'll take a little bit of pressure off the lectures. So anyway, so we'll start off right away in section 1.1, Intro to Linear Systems, and see how it goes. So today, I am by myself in this room, so nobody can catch my silly mistakes. So I'll try to not make too many silly mistakes. So let's start at 1.1.1. And we have a linear system, x plus 2y equals to 1, and 2x plus 3y equals to 1. So those are our two equations, and we have two unknowns, and we're looking for the answer. So this is a good warm-up. So what do we do? Well, we will subtract the first equation from the second equation by with a factor of 2. Right? So negative 2 times the first subtracted from the second. So first equation stays the same. Right? And then we have 2x minus 2x, so the x's go away. We have 3y minus 4y, right? And on the right-hand side, we have 1 minus 2, which is negative 1, hopefully. All right, so we have x plus 2y equals to 1, and negative y equals negative 1. All right, so of course we can then solve for y. So y is 1. And then we can plug that value for y into the first equation, right? So this says that x is 1 minus 2y, which is 1 minus 2, which is negative 1. Right, so our answer is, of course, negative 1, and y is 1. And the beauty of linear algebra is that most of the time you can check your answers, right? So if we take this and plug it back into our original equation, things should work out, right? So we have x, which is negative 1, plus 2 times y, which is 1. So negative 1 plus 2, which is 1. And of course, that matches. So that's good. Then we have 2 times negative 1 plus 3 times 1. So negative 2 plus 3 equals to 1. And that matches, right? So that means that we have some confidence in our solution. Right, so that's a good one. Okay. So if you watch the whole stream online, you get to see me erase a lot. But if you just skip through the stream with the bookmarks, like by the numbered problems, then you don't have to see me erase stuff and talk to myself while I'm erasing things. Maybe that's good entertainment, I don't know. go. So our next problem is more of the same. So 1, 1, 3. We are given two equations, 2x plus 4y equals to 3, and 3x plus 6y equals to 2. All right, and we're looking for solutions. So there are a couple of ways to go about this. What we can do is we can divide the first equation, right? So divide by 2, right? So that gives us x plus 2y equals to 3/2. And if we divide the second equation by 3, right, then we get x plus 2y equals to 2/3, which is kind of weird, right? Because if we have some values for x and y, then 2x plus 2y takes some value, and that value better be the same in both of these equations, right? So in this case, since 3/2 is not equal to 2/3, it's been a long summer, right? But hopefully we realize that that's not the same. It means that we have no solutions. No solutions. Now, so that was pretty straightforward here, because when we divided by the leading value here in the two equations, we ended up with the same equation on the left for both of them in different right-hand sides. Kind of the standard route to go about this is, well, you still eliminate. So this is the second way of doing this, right? So we have the first equation, and what we do is we subtract an appropriate amount of the first equation from the second, right? So if we multiply by 3/2 and subtract, right, then we will eliminate the x value, right? Because then we have 3 minus 3/2 times 2x, and we have plus, we have the 6, and we're subtracting 3/2 times 4y, and that equals then 2 minus 3/2 times 3. So if we clean that up, what do we get? Well, the 2's cancel, right? So then we have 3 minus 3, which is 0. So we have the first equation, of course, stays. Then we have 0x plus 4 divided by 2 is 2, right? And 3 times 2 is 6, so 6 minus 6 is 0. So we have 0y. So that whole equation goes away. And over here, what do we have? We have 2 minus 9/2. And if we write 2 as 4/2 minus 9/2, then we have 5/2. Hopefully I got that right. Bottom line is that that's something non-zero, right? So here, so if we clean up this, that's 0. So what we have is 0 equals to something non-zero. Right, which is strange, right? So if we ever eliminate a system, we solve a set of equations, and we end up with one row that's saying 0 equals to something non-zero, that doesn't make any sense, and that indicates that we have no solutions. Right, because that makes no sense. So that's sort of the generic way of finding out that we have no solutions, right? So this problem, the equation was sort of simple enough, but by dividing by the leading integer in each equation, we got the same, and we got this thing here, right? So these are kind of equivalent ways of identifying that we have no solutions. Right? So we get some numerical value equals to some other numerical value which is not the same. And if that held, all of mathematics would just fall to the ground and be gone. Anyway, so that takes care of 113. And we're back to erasing. Okay. All right, next problem is 117. Still more of the same, except now we have three equations and we have three unknowns, x, y, and z. So you have x plus 2y plus 3z equals to 1. X plus 3y plus 4z equals to 3. And x plus 4y plus 5z equals to 4. So those are three equations, and we're looking for the values of x, y, and z if there is a solution. So this is pretty friendly. Right? So what we will do is we will subtract the first equation from the second. Right? And we will subtract the first equation from the third, right, to get rid of the x values in the second and third equation. So let's do that. So the first equation stays the same. Then we have 1 minus 1x, which is 0. Like 3 minus 2y, so that leaves us a y. 4z minus 3z leaves us a z. And 3 minus 1 is 2. Third equation, the x's go away. We have 4y minus 2y, so we're left with 2y. 5z minus 3z leaves us with 2z. And 4 minus 1 leaves us with 3. Okay. Then what's our next step? Well, we're looking for the values of x, y, and z, right? So now we only have x in the first equation. Wouldn't it be nice if we then only had y in the second equation? So what we're going to do is we will subtract the second equation from the first, right, with a factor of 2 to get rid of the y's, and we'll do the same thing. We'll subtract 2 times the second equation from the third equation. So that's the plan. So that's a good plan. I'm going to do it in the opposite order, right? So the middle is not going to change. And what happens in the bottom row, right? So we'll be subtracting 2y from 2y, so the y's go away. And then we're subtracting 2z from 2z, so the z's go away, right? So nothing survives, actually we get a 0 here. And then we're subtracting 4 from 3. So the bottom here gives us 0 equals to something that's non-zero, right? So that tells us that we have no solutions, right? So there's no hope here. Now, sort of in general, right, we would have continued to subtract 2 times the second from the first. So let's just do that, see if I can get my algebra right. So the x stays, right? Then we're subtracting 2y, so the y's go away. We're subtracting 2 z's. So 1 z does indeed survive. And we are subtracting 4 from 1, so we get -3, right? So what if something had survived here, right? So now what we have done in general, right, so we only have x in the first equation. We only have y in the second equation, right? And if the z had survived, what we would have done is we would have subtracted appropriate amounts of the third equation from the first and second, so that we would only have z in the third equation, so we would get the answer, right? But here, that's not possible, right? So we have a system of equations which has no solutions. So another way of saying that is that we have an inconsistent system of equations, consistent system of equations, right? So we have no solutions. Okay, so that takes care of that problem. Okay, Next up, we have a similar problem. So we are in 1,1,14. So again, we have a system of three equations with three unknowns, x, y, and z. So it's x plus 4y plus z equals to 0. 4x plus 13y plus 7z equals to 0. 7x plus 22y plus 13z equals to 1. So we play our usual game, right? So we're trying to get the values for x, y, and z. So we want to separate the values, right? So we will take the first equation, multiply by -4, and add to the second, or multiply by 4 and subtract from the second, depending how you want to phrase that. And we take -7 times the first and add to the third, so we get all zeros for the x values, right? So let's see. First equation stays, unless there is some strange typos. 4y plus z equals to 0. Then let's see, 4 minus 4 is 0. Then we have 13 minus 16, right? So we get -3y. Then we have 7 minus 4. So that gives us plus 3z. And the 0 stays, right? Because we're subtracting 0 from 0. Let me just make sure that my notes agree with me. So far, so good. Okay, the x's go away. We have 22 minus 14 minus 28. So minus 6y. And then we have 13 minus 7. So that leaves us with 6, right, 6z, and the 1 stays because we subtracted 0 from it. So then we can definitely simplify things, right? So here we have the same coefficient, right? Never mind the sign, right? So let's divide by -3, right? So anytime you can simplify stuff, that's a good thing, right? Because the numbers kind of carry through and you don't want them to get out of control. So let's do that. 4y plus z equals to 0. Then we have y minus z equals to 0. And let's just, we can divide this by -6, why not? Sometimes that's useful. Now we're creating a fraction, and in this case it's not going to be a big deal, but lots of times if you can avoid generating fractions, it's easier. Like, at least my brain works better on just integers than on fractions. But if your brain is different, that it works better on fractions than integers, go ahead and generate fractions. All right, so what do we get? We get y minus z equals to -6. All right, so we can already smell that something bad is happening, right? So if we just follow our standard recipe, we are going to take the second equation here and we're going to subtract it from the third, and we would also subtract it times 4 from the first. But this piece here, right, is the critical piece, right? So let's not modify the first equation just yet. Right, so we have y minus z equals 0, and then we get 0 equals to -6, right? So, of course, this is our problem. 0 equals to something non-zero indicates that this problem has no solutions. Right, so again, we had an inconsistent set of equations. Okay, so that takes care of that problem. Okay. What is next? Oh, this is a fun one. Definition of fun may vary, but I think this is fun. This is number 19. We have, again, a system, the 3 equations. Start to feel kind of familiar. So we have x plus y minus z equals to -2. 3x minus 5y plus 13z equals to 18. Then we have x minus 2y plus 5z. Then here comes the kicker. This equals to some value k. So k here, is a parameter. So this is the parameter k. And what do we want to do? Well, we want to solve this for all values of k. So the question is to solve for all values of k. So we're like, well, what does that mean? Right? Slight panic attack. Well, we're just going to do our usual stuff, right? So for now, we're just thinking of k as a representative for some value. And we just go ahead with our usual tactics and try to separate the variables, right? So we want to take 3 times the first equation, subtract from the second, and 1 times the first equation, subtract from the third, to get rid of the x's. All right, then you see what happens. So the first equation stays. X plus y minus z equals to -2. Of course, the x values go away. We have negative 5 minus 3, so we have negative 8y. Then we have 13, subtract 3 times negative 1, so we end up adding 3, right? So it's plus 16z equals to 18 plus 6, 24. Hopefully my notes agree. That's good. Like adding integers when you're by yourself in a room is really hard sometimes. We get rid of the x's in the third equation. We have negative 2y, subtract y, so we have negative 3y. We have 5z, and we end up adding another z because we have two minus signs, right? So plus 6z. And what do we have on the right-hand side? Well, we had k, and we're subtracting the first equation, so we're subtracting negative 2, so we end up with k plus 2. So far, so good. Then we want to simplify a little bit, so I'm going to divide second equation by negative 8, and the third equation by negative 3. Right, and what do we get? First equation stays. Then we get y minus 2z, right, equals to negative 3. All the signs flip. We divide by 8. Third, we get y minus 2z. And on the right-hand side, we get negative k plus 2 over 3. Right. And my notes still agree. So what can possibly go wrong? Well, we see we have the same quantity here. So if we play our usual game, right, then we will take the second equation, we will subtract it from the third, and we will subtract it from the first. So let's go ahead and do that. So then we have x. We're subtracting y from y, so the y's go away. We have negative z, we're subtracting 2z, so we end up with a positive z. Right, and we have negative 2, we are subtracting negative 3, so we end up with 1. Right, so x plus z equals to 1. Second equation stays, right, y minus 2z equals to negative 3. And of course, this is where all the fun happens. Everything cancels on the left-hand side, right? So we have 0 equals, what is it equal to? Well, we have whatever is sitting here, and then we're subtracting negative 3, right, which means that we're adding 3. So we end up with 3 minus k plus 2 over 3. Let's make sure that I agree with myself. Yes. So now, if this says 0 equals to something non-zero, we would have no solutions, right? So if, well, I should say 1, right, because k is a parameter here. So when k is such that 3 minus k plus 2 over 3 is non-zero, we have no solutions. So that's case 1. And case 2 is when 3 minus k plus 2 over 3 equals to 0. And we have solutions. So we have solutions. Alright, so part of our answer, right, is like we have to solve for k here. So let's do that. Kind of our little side box here, or middle box. So what do we do? Let's multiply through by 3, right? So we have 9 minus k plus 2 equals to 0. Let's have a parenthesis there, so we get things right. So we end up with 7 equals to k, or k equals to 7 is the critical k value. Right? So if k is not equal to 7, we have no solutions. But when k equals to 7, we have solutions. Right? Because if k is 7, right, so if we continue with that case, then what's sitting here is 0. Right? So the bottom equation then says when k equals to 7, it says that 0 equals to 0, which is true, but it doesn't add any information. Right? So what we're left with in this case, we have two surviving equations. Right, so these two equations survive, but we have 3 unknowns. So what do we do? So let's do some cleaning here so we can continue. So all of the rest that's happening is happening in the context of k being 7, right? Because if k is not equal to 7, there are no solutions and the problem is done, right? So the issue we have at this point is that we have 3 unknowns, x, y, and z, and we have 2 equations. Right? So it turns out that we actually don't have enough information to get unique values for x, y, and z. Right? So we can rewrite this in a number of ways. So we can write this as x equals 1 minus z, and y equals negative 3 plus 2z. So we're just moving z to the right-hand side. So here we're calling x and y, they are our leading variables. Right? It's a little bit of language here. So these two here are leading variables. And z, that we moved over here, is what we call a free variable. And we're going to talk more about this in lecture and going forward, but I just want to kind of toss in the terminology right away, because why not? So what do? When we have a free variable, what we tend to do is we introduce another parameter, right? So a new parameter. So you pick your favorite letter of the alphabet. Let's pick T this time. And we say that Z equals to this parameter, right? And this parameter can take any value we want, right? So you can run all over the real line. So in our class, at least 95% of the time, we're only dealing with real variables, right? So we may do some complex stuff in the very last week of the semester. But for now, this is just something that takes real values. So it's values between negative infinity and positive infinity. All right, so with this, we can write x, right, as 1 minus t. Y is negative 3 plus 2t. And z is t. All right, so we can write it in this way. Notation that we will use going forward, we'll say that x, y, z collected in a vector. Well, it takes the values, of course, 1 minus t, minus 3, 2 plus t, and t. And we can break this into one piece, which doesn't depend on t. All right, so 1, negative 3, and 0. And then we have the stuff that does depend on t, which is negative 1, 2 for y, and 1 for z. So we can write it in this form, we can write it in that form, and I think at this early stage, the book writes it as x, y, z, in a collection like this, so 1 minus t, minus 3 plus 2t, and t, right? So essentially we can write it as a system of equations with a parameter, we can write it as in vectorized form, or we can write it as a triplet of values. Right? These are all equivalent. The different notations are sort of useful in different contexts, and the context of our class will be most useful going forward is to collect it in this way. Right? So when k is 7, I to summarize things, what happened? Well, we have solutions. We don't have one solution. We have infinitely many. Infinitely many solutions. Right, so because t here can range from negative infinity to positive infinity, right? And whatever quantity we're adding to this anchor point is also a solution. So that's kind of interesting, right? And if we think of x, y, and z as being like locations in 3 space, right? So x will be some direction over here, y is direction like in that direction, and z is the height of the room. Then what this is, well, this is a point in 3 space, right? And this is a line going through that point. So we have infinitely many solutions running through this point, pointing in that direction. And we'll talk much more about that going forward, but we can always interpret these solutions in a sort of a geometric fashion. Anyway, so we have seen examples at this point of systems of equations with one solution, no solutions, and now in this case, infinitely many solutions, right? So that ends 1.1.19. Okay. This board is not so easy to erase at all. Their writing really sticks. Okay, let's see, what do we have? I have a couple more problems than 1, 1. Next one is 1, 1, 21. So we're not given a system of equations here. We're given the scariest thing of them all, which is the word problem. It doesn't have a lot of words in it, right? But it says that the sum of any two of three numbers are 24, 28, and 30. Find the numbers. Find the three numbers. All right, so we're looking for three numbers. So we can call them anything we want. And what do we know? Well, if we add them pairwise, we end up with these sums. Right, so if we're looking for all possible pairs of three, right, it means that we're leaving one out. Right, so we can call our numbers Adam plus Bravo. Right, so if we add those two, we get 24. If we add Adam and Charlie, we get 28. And if we add Bravo and Charlie, then we get 30. So that's maybe not the easiest naming convention, right? But the letters or the names, they don't matter, right? They're just placeholders for numbers, right? So don't get fixated on the fact that we're using X, Y, Z or A, B, C or whatever. They're just placeholders for numbers. So I'm going to switch to A, B, C here. Right, so we have A plus B is 24, A plus C 28, and B plus C being 30. So then we would do our usual stuff. Right, so we will subtract the first equation from the second, so then the A only survives in the first equation, right? So we have A plus B equals to 24. The A goes away, we're subtracting a B, so we have negative B plus C, and we have 24, or 28 minus 24, which is 4. And we have not yet touched the second equation. So we have B plus C equals to 30. Then we're going to do our standard stuff. So we're going to get rid of B. in the other equations, right? So if we add the second equation to the third, we will get rid of this b. And if we were to add it to the first, we would of course get rid of that b. So for now, I'm going to defer changing the first equation and kind of talk about that when we're done. So it's sometimes useful to do it in this way. So minus b plus c equals to 4. Then we have added negative b to b, so that goes away. We're adding c to c, so we have 2c, and we have 34. Okay. So then, what do we do? Well, I'm going to divide this by 2, right? And I'm starting to feel lazy. So this just then turns into c equals to 17. So that is then part of our solution, right? So c takes the value 17. Then if we look at the second equation, b here now only depends on 4 and c, and we now know the value of c, right? So we can take this and plug into the second equation. So that says that negative b equals to 4 minus c, right? So that's 4 minus 17, negative 13, right? And of course, that means that b should be 13. Right, so that's also part of our solution. And then we can plug the value of b into the first equation, right? Because this, of course, says that a is 24 minus b, b being 13, that better come out to be 11. Right, so a equals to 11. Right, so if we are eliminating, variables here, but we don't necessarily push up, we only eliminate down, we end up with a system where, if we have a unique solution, you can read off the last variable in the last equation, and then you can take that information and sort of propagate up. So that method of solving is known as back substitution, right? So back or backward substitution. So when you solve things by hand, that's kind of useful, I think, because in the backward substitution step here, we're plugging numbers in, right? Whereas if we go to the full elimination, if we had eliminated b from here, then that would, of course, by adding this equation here, well, we'll get rid of the b, but we get a c. And then once we have the c here, we would have to go back and eliminate, right? So it's more work, and you're working with multiple variables, so there's sort of a higher probability that you make mistakes, right? So by doing it in this way, you can save a little bit of computations, and the computations that are at the end are all with explicit values. So that may eliminate some mistakes, which is good. So the claim, right, is that our answer, the three values are 11, 13, and 17. right? And we can check, and I think the problem demands that we check, but that's always the beauty of like solving linear systems. Once you have the answer, you just plug the answer back into the original equations and see what happened, right? So we have 11 plus 13, which is 24, and that matches, right? And we have 11 plus 17, which is 28, that matches. And we have 13 plus 17, which is 30, and that matches, right? So indeed, we have the right answer, right? So the three numbers we're after are 11, 13, and 17. Okay. Okay. So we have 1, 1, 42, and it has an A and the B part. So in part A, we have, let's use the same notation I have here. Yep. We have x1. Let me just write all these out. So we have negative 3 x1. We have x1, negative x1. We have plus x2 plus 2x2 plus 8 x2. Here we have plus x3 minus 5 x3 plus x4. So then we can line up the equal signs, because equations have to be pretty. Right? Pretty equations are easier to solve than ugly equations. I think that's a theorem. Okay. So this kind of goes back to the way I solved the last problem, right? So we have here a system where, x1 is lonely in the first equation. The first time x2 appears is in the second equation. The first time x3 appears is in the third equation, and x4 appears in the fourth equation, right? So we kind of have this structure. It's a triangle. So this is known as a lower triangular system. And for part B, let's just write this out right away. We have something similar. Let's see if we can. It helps if you look on the right page of your notes. Otherwise, things get very strange. So we have x1 plus 2x2 minus x3 plus 4x4 equals to -3. Then we have x2 plus 3x3 plus 7x4 equals 5. We have x3 plus 2x4 equals to 2. And finally, we have x4 equals to 0. Right, so again, we kind of have the opposite setting, right? So x1 only appears in the first equation, and then x2 is the leading in the second, x3 is leading in the fourth, etc. Right? So we also have a triangular system, except in this case we have an upper triangular system. And usually that's what we're aiming for when we eliminate by hand, right? So we take the first equation, we subtract from the second, so that we get rid of the first variable in the second equation. So here, instead of calling the variables x, y, z, we just number them, x1 through x4. And a lot of times if you have lots of variables, that's sort of the most convenient thing to do. So if we have a triangular system, we can use this idea of substitution, right? So in the lower triangular system, we can use forward substitution. And in this case, we can use back or backward substitution, like we did in the previous problem. So what does that mean? Well, the first equation, right, it tells us that x1 is -3. Then we take the second equation, right, so then we have x2, and x1 is known, so we can move that to the right-hand side, right? So we have 14 plus 3 times x1, right? So that's 14 plus 3 times -3, so this being -9, so x2 is 5. I'm going to check my notes so I agree with myself, so things don't get out of control. So my notes agree. x3, we go to the third equation, x2 and x1 are now known, right? So we have 9, subtract x1, subtract 2x2. So we have 9 minus -3 minus 2 times 5. 9 plus 3 is 12, subtract 10 is 2. Do my notes agree? Yes. And finally, x4, like we get here, x1, x2, x3 are known. So we have 33 plus x1, because of the minus sign, subtract 8x2 and add 5x3. So what is this? It's 33 minus 3. X2 is 5, so we're subtracting 40, and then we're adding 10. So that's 30 40, subtract 40, so that's 0. All right, so we get a solution where x1, x2, x3, x4 take the values -3, 5, 2, and 0. -3, 5, 2, and 0. My notes agree. All right, so that's the forward substitution method. And then we play the same game over here, except we go from bottom up, right? So first we have that x4 is 0. Then we'll go to the third equation. x4 is known, right? So x3 is 2 minus 2 x4. I can subtract 0 from 2, I think, and get 2. Then we go to the second equation. x3 and x4 are known. So we have 5 minus 3 x3 minus 7 x4. We have 5 minus 6, -1. Never hurts to check your algebra. 2, -1, yes. And nothing is harder than doing live algebra. It's, when you sit in the audience, it looks simple, right? But when you're doing it, it's always harder than it should be. So we're in the first equation. These are known, so we move into the right-hand side. So we have -3 minus 2x2 plus x3 minus 4x4. So we have -3 plus 2 plus 2 minus 0. Right, so that should come out to be 1. So we have a solution where x1 is 1, x2 is -1, x3 is 2, and x4 is 0. Right. So if you're given a system that is either in lower or upper triangular form, life is pretty friendly, pretty straightforward. So that takes care of 1.1. So we have a little bit of time to do a couple problems in 1.2. This is a good workout. I don't know what sport is for. It's like the window washer Olympics or something. Okay. Okay, so we are moving into 1.2. Let's start with 1, 2, 1. So it's really just a continuation of 1.1 solving systems, getting used to the matrix vector notation and sort of leaving the systems behind in some sense. So problem 1, we have x plus y minus 2z equals to 5. We have 2x plus 3y plus 4z equals to 2. So we have two equations, right? We have three unknowns. So it means that we cannot guarantee that we have a unique solution. So one of two things is going to happen. So we will have either no solutions or infinitely many solutions. Right, those are the only two possibilities here. And we're going to quantify that going forward. But since we have a mismatch here of number of equations and unknowns, we're guaranteed that one of those things is going to happen. So, what do? Well, we use our same old trick. So we take the first equation, subtract 2 times first equation from the second to get rid of x in that equation, right? So first equation stays. We have x plus y minus 2z equals to 5. The x's go away. We have 3y minus 2y, so that gives us y. We have 4z, subtract negative 4z, right? So we have 8z. And we have 2 minus 10, so negative 8. Okay. And now in this case, we're going to go forward and subtract the new second equation from the first to get rid of the y term. So then we have x, the y goes away. We have negative 2, we're subtracting 8. So we get negative 10z. We have 5, we're subtracting negative 8, so we're adding 8, so we get 13. And here we have y plus 8z is negative 8. Okay. Either my notes and this is right, or they're both wrong in the same way. I think I got my minus signs right. So that's as far as we can get. Right, so we have, again, this scenario where we have x and y sort of separated out from everything else, right? X only appears in the first equation, y only appears in the second. Z is hanging out all over the place, right? And we can't get rid of it. So these two are what we call leading variables. And z, it's the same z, it's a free variable. So what we do in the case of a free variable is this. So each free variable, here there's only one. Well, but each free variable gets a parameter. Last time we picked our favorite letter of the alphabet to be T. So let's pick something else this time. So this time, let's pick from the Greek alphabet. Let's pick alpha. So we have that Z equals to alpha. And we can express X, right, as 13 plus 10Z, which of course is then 13 plus 10 alpha. And Y is negative 8 minus 8Z, or with the parameter negative 8 minus negative 8 alpha. So if we collect that, we can write X, Y, and Z, right, everything in terms of alpha. Right, so we have X being 13 plus 10 alpha, Y is negative 8 plus negative 8 alpha, and Z is alpha. And again, we usually like to split out the constant and the variable part. So we have the constant part being 13, negative 8, and 0. Then we have the alpha dependent part, right? So alpha is multiplied by 10. For X, it's multiplied by negative 8 for Y, and multiplied by 1 for Z. Right, so those are our solutions, where again, alpha can take all the values in R, right? So anything between negative infinity and positive infinity, right? So in this setting, we ended up with infinitely many solutions of this form. So again, it is sort of geometrically in 3 space. It's the straight line going through this point in that direction. And we'll do some plotting of that going forward. My hand drawing skills are a little questionable, so I'll skip that embarrassment for now. So that's 1, 2, 1. We still have a little bit more time. Okay, so let's do similar problem. 1, 2, 3. So what I'm going to do a partial erase here. Well, it's like a 90% erase. I'm just going to leave that up here. Okay, so we have 1, 2, 3. And we have a system of equations, x plus 2y plus 3z equals to 4. I think somebody got their finger stuck on the keyboard. 1, 2, 3, 1, 2, 3, 4. So that's the whole system. It's kind of small, right? So we have one equation, but we have 3 unknowns. So again, if we have more unknowns than we have equations, we're going to end up with either no solutions or infinitely many solutions. In this case, if you only have one equation, you're actually guaranteed to have infinitely many solutions, right? So here, we are going to have infinitely many solutions because we have one equation, more than one unknown. So what do we have? Well, there's no elimination to be done because it's already done for us. So x, that's our leading variable. That's a strange L, leading variable. And y and z are the free variables. And then we have this statement which did not get erased from the previous problem, saying that each free variable gets a parameter. So we're going to have z being some favorite variable. Why not beta? And z, should we stick with the Greek alphabet? Well, why not? Gamma. Right. And of course, we can write x as 4 minus 2y minus 3z, or in terms of the parameters. So we have two parameters. And both beta and gamma can take all values in R, right? So from negative infinity to positive infinity. So 4 minus 2 beta minus 3 gamma. So we can write the solutions to the set of equations x, y, z, but in terms of the parameters. So x is 4 minus 2y minus 3z, where y is, wait a second, the caffeine level in my brain has shrunk, it's diminishing, I can't think anymore. So it's 2 beta minus 3 gamma, y is beta, z is gamma. And then we play the same game. So we split out first the constant part, right? So whatever is not depending on beta and gamma. So x gets the 4. There's nothing for y and z. Then we have the beta dependence. Right, so x depends on beta with a factor of -2. Y depends on beta with a factor of 1, because hey, y is beta. But z does not depend on beta, so that gets a 0. And then we have gamma times x has a factor of -3. Y only depends on beta, so we get a 0. And z is gamma, so that gets a 1. So we have infinitely many solutions. Again. But we have two parameters here. So if you want, like each one of beta and gamma can take infinitely many values, right? So it's sort of infinity squared. I'm not going to write that on the board because some mathematician may see it, right? But it's definitely more solutions, right? So again, if we think in 3 space, this is some point in 3 space. You're sitting at 4, 0, 0. Each one of these corresponds to a line pointing in some particular direction of that point, and So this paints a line in some direction going out to infinity. Maybe say this is the point, the line is going like that. Now, the other line is going in some other direction. And if you take all combinations of beta and gamma, geometrically, this will be a plane going through this point, right? So the geometric interpretation it's a plane, which is something that's two-dimensional, going through the point 4, 0, 0, and all of this is happening in R3, like in 3 space, right? So that's one way to geometrically think about what that solution looks like. I think that's a good place to call it a day. So that's that. Thank you very much.